Hello again. This is Newtonian gravity, part 5. In part 4, we found that the gravitational potential energy is now equal to, for an object and Earth. So negative g times mass of the object times mass of the Earth divided by r, which is the distance between the object and the center of the Earth. Now, this applies for all r, whether you're close to Earth or really far, as opposed to the formula you used to use before, which was mgy or mgh. So how are these related? Okay, so assume you drop an object from some height, initial height, h. So this is your initial point, and it's going to hit the Earth over here. Here's the center of the Earth. RE is the radius, and at a given time, the object is r away from the center of the Earth, the same r that I use in the formula. Okay, so let's write down the change in the gravitational potential energy. Delta U will be U final minus U initial. So it's equal to, I'm going to use the formula, new formula, negative G M Earth over, at the final position, the radius becomes RE, radius of the Earth. Okay, that's the first term, UF, minus from delta, and then write it again for I now, for the initial position. Negative G times ME again, these constants, divided by RI, which is H, which is just H. Okay, H is the altitude, measured from the surface of the Earth. Now, this formula is exact. All right, so let's simplify it a little bit by first factoring out G, M, and capital M. So we have now here 1 over H minus 1 over, okay, I made a mistake here. It's not H, but it is H plus RE, sorry. RE. We're measuring from the center of the Earth, remember? Sorry about that. So this is also 1 over H plus RE minus 1 over RE. Okay, sorry about that. So equals now G M ME. So here I have RE minus H minus RE in the numerator. In the denominator, I have H plus RE times RE. Okay, so these two go away. H is the height. Now what if H is really small compared to the radius of the Earth? In that case, since you have this summation here, H plus RE, in that case, H plus RE will be RE. That's our approximation, all right? So 1 meter versus 6,000 kilometers. All right, so delta U in that case will be equal to negative G M E H divided by, there are two RE's in the denominator, so RE squared. Okay. Now I want you guys to remember, oops, didn't mean to do that. Okay, let's go back. Okay. I want you to remember this quantity here. We have G, excuse me, G, we have RE squared and M. All right, so here, G times ME divided by RE squared. All right, that is a little g, the acceleration due to gravity. This was in part 2. So that is g times m times h with a negative. So you get here negative mg h. Indeed, when an object falls, its potential energy decreases by exactly by that amount, mgh. If this approximation is valid. For small h, you can do that. For larger h, okay, if you're working with, I don't know, space physics or something like that, you can't do it anymore, okay? So you have to go with the most generic formula. So this applies to, the new formula for gravitational potential applies to satellite problems or the motions of planets around the sun. Okay, so let's take a look at these. For instance, when we did projectile motion in class, there were a couple of assumptions we made. The first thing is, if it's a football field, it's not large enough. So for that distance, Earth is flat. So you kick a football, it follows a parabolic path because gravity is always downward. This is the gravitational field, which is downward. That's why we call it parabola. The motion under that potential, the original one, with a varying g, is actually an elliptical motion. The path will be an ellipse instead of a parabola. So if you have Earth here again, let's draw an Earth. All right. Gravity field is to the center around the Earth in all directions. It always points to the center of the Earth. Okay, so if you kick the football here in Houston this way, yeah, for short distances, that approximation is fine, which is just a parabolic path, flat Earth, as some people claim, right? But if you kick the ball faster, so fast, now it crosses border, it goes to Louisiana, and then you kick it faster, goes to Florida, and then Atlantic Ocean, okay? If you can kick it fast enough, it's gonna go all the way around the Earth and maybe hit you back, all right? Throw it faster than that, now you leave Earth, and it's possible. Okay, so that velocity is called the escape velocity. That initial velocity, if it is large enough, we call it the escape velocity. You leave Earth, all right? So let's find that. Let's find that velocity for a planet with radius r and mass m. How do we do that? We use the new form of the energy. So the potential energy. We also have kinetic energy in the beginning. So when you kick it, you have the kinetic energy, 1/2 mv squared. In this case, we call it the escape velocity, plus the potential energy, which is negative g m times mass Earth divided by the radius of the Earth, because you're at the surface. This little r is RE. This is the mechanical energy. and it will be conserved. Gravity is the only force we're working with. It's a conservative force. And the relation between the work done by gravity and the gravitational potential energy. You saw that already in the previous video. So this is conserved. The change, there won't be any change in the mechanical energy. E mechanical. This means that over here, when you're far away from Earth, E is still the same, whatever you had in the beginning. This. So if I write 1/2 mv escape squared minus g times m mass of the Earth over re, this is the constant that never changes. So when you're over here, when you're a certain distance, let's say r away from the center of the Earth, this is r at this point, that's where your speed will be different, mv squared, slower, but your gravitational potential energy will be negative g m me over that r. Okay, so your r increases, your v changes accordingly, but the sum of the two terms remain a constant. What is that constant? Okay, so imagine you do this, you take r all the way to infinity, practically a distance really far from Earth, okay? You don't have to take it really to the infinity, but really far, so far. If you do that, of course, 1 over r becomes 0. All right, at that point, do you really need the object even moving, okay? You don't, because we're looking for the minimum velocity, which is enough to escape Earth, okay? Anything above that will be okay, but what is the minimum? So at this range, at infinity, you can take v also equal to 0. So what do you have now? 0 plus 0, 0, which means E is 0. If E is 0 at infinity, it was 0 at an intermediate point. It was 0 in the beginning, all right? So this term here, 1/2 mv escape squared minus g times m Earth over re, that is 0. All right, so solve this for v escape, m's go away, and if you solve it for the escape velocity, that's 2 times g times mass of the Earth divided by radius of the Earth. All right, let's find this in number. G, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared times Earth's mass. I remember it was 10 to the power 24 kilograms. Was it 5 point? What was it? Let me see. Just give me a second. Planets table. So how about this one here? Okay, that's good. So let's use this. Earth has a mass of 5.98. Yeah, 5.98 times 10 to the 24th power. in kilograms, and now divided by the radius of the Earth, 6.38. 6.38 times 10 to the power 6 meters. All right. Okay, so punch in the numbers now. 2 times 6.67, 10 to the negative 11, times 5.98, 10 to the power 24, divided by 6.38, 10 to the power 6. Take the square root of that. 11,181.966. So it's 11,182, let's say, meters per second. In 1 second, 11 kilometers. That's so fast. Let's convert it to miles per hour, if you will. So 1 mile is 1,609 meters. And in 1 hour, there are 3,600 seconds. So this number times 3,600 divided by 1,609, 25,000 miles per hour. 25,019 miles per hour. I don't think we have a gun right now as fast as this. Maybe we do, but that's the escape velocity you'll need to escape Earth. It was Jules Verne's idea, you know, the 19th century science fiction author, Jules Verne. He wrote a book called From the Earth to the Moon. And in that novel, he had the idea of sending people to the moon with a cannon. Okay, so I use a capsule. All right, so this guy here, use the capsule and put the capsule in the cannon, large cannon. Probably he couldn't imagine how far or how long that cannon would be. Okay, here is another picture. So he thought about building a large cannon like this, and let's calculate the length of this cannon. All right, so how are we going to do that? We need that escape velocity, 11,182 meters per second. Now, when you're inside the capsule, you want well, there will be acceleration, like constant force at least, gives you constant acceleration. You know, the pilots, when do their acrobatics, sometimes, you know, they can pass out. Human brain can only withstand a certain number of G's, right? So let's say you start with initial speed 0, and when the capsule leaves with this velocity, okay, you want to be awake. Okay, so let's say for a comfortable ride, the acceleration should be around, let's say, 10 meters per second square. That's close to G, right? So it's as if you're lying on your back, right? That's the feeling. Of course, this will be in addition to the Earth's existing gravity, but let's say this is reasonable, okay? The question is, what will be the length of this cannon, okay? Can it be done with a cannon like this, or I don't know how long this is, but let's find that. So let's call it L, the length of this cannon. How do we do that? Let's use the kinematics equations. V final squared is equal to V initial squared, or V0, plus 2A acceleration times the displacement, delta x, or L in this sense, in this case, L. This is 0, initially at rest, so A is 10. L will be the square of 11,182 meters per second squared divided by 2A. 2 times 10 meters per second squared. Not squared, yeah, meters per second squared. So let's do it. 11,182 squared divided by 2, or 20 divided by 20. Okay, so that is 6.25, not meters, not kilometers, 6.25 million meters. Okay, so times 10 to the 6th power. In meters, compare this to the table we have here. Okay, now look at the radii of the planets there. Okay, well, you can build this maybe on Earth, which is a radius 6.38, a little bit larger than this L. Okay, so you have to dig a really deep well on Earth. All right, so this is where you exit. This is where you start, the center of the Earth. That's where you start, and with a reasonable acceleration, by the time you reach the surface of the Earth, you're going to have that escape speed. Okay, you have to go to the center of the Earth. So you have to check for another novel. Actually, Jules Verne did that too. Probably he wasn't even thinking about these calculations, but he wrote a book called, what is it, Journey to the Center of the Moon, Center of the Earth. Jules Verne, Center of the Earth. Yeah, so. All right, so apparently the center of the Earth had some large reptiles, prehistoric creatures. Okay, so let's open up a new whiteboard. Let's just clean everything here. Clear canvas. What is the fastest thing in the universe? That's light. Speed of light is approximately 3 times 10 to the power 8 meters per second. So 300,000 kilometers per second. What if the escape speed is c? C stands for speed of light. Speed of light. Okay, so what if the gravitational field is so strong near the boundary of a region in space that the escape velocity is c? Okay, just using classical Newtonian physics now, but hypothetically, if this happened, since nothing can move faster than light and nothing even can approach the speed of light, nothing massive, nothing will escape the planet or the star or whatever that object is, right? Actually, we have a name for such objects. When even light cannot escape, we call them black holes. All right, so that formula that says escape velocity is square root T, not G, 2 G M over R, where M and R are the parameters of that star or planet. What if we take the escape velocity as C? And Let's take M to be mass of the sun, which is about 2 times 10 to the power 30 kilograms. Okay? So we know G, M is given, C is given. We can solve for R. So if I were able to squeeze sun to a smaller size, what should be the size so that the sun acts like a black hole? All right? That's the, at least classical way of solving this issue, this problem, okay? So 2gm over r would be equal to c squared, solving for r, 2gm, okay, mass of the sun. The symbol for sun is this, and the symbol for earth, I think, is this. So the mass of the sun is going to go here, divided by c squared. 2 times 6.67 times 10 to the negative 11 times 2 times 10 to the 30th power for mass. Divide this by c squared. 3 times 10 to the power 8 squared. Okay, so 2 times 6.67, 10 to the negative 11 times 2, 10 to the power 30, divided by 3, 10 to the power 8 squared. Okay, this is 2,964 meters. It's about 3 kilometers. Okay, 3 kilometers. If you can squeeze the sun to this size, which is much smaller than Houston, much smaller, then it will be a black hole. Even light cannot escape from a black hole. All right. At the heart of every galaxy, we have these supermassive black holes. That's what we know. And recently, one black hole like that was, for the first time in history, observed and photographed. All right. Okay, so that's black holes. What about regular objects, like comets? Okay, so comets are going around the sun in elliptical orbits. All right, not bad. Okay, here's the comet. I didn't want a triangle there. Okay, so the comet is r away from the sun. Now, this is not a circle, but an ellipse. So for ellipses, do you guys know the formula for ellipse? An ellipse has 2 focal points, one here and one there. All right. So the thing that makes this an ellipse is the fact that if you add the distances from the focal points, in this case, r plus, let's call this d, r plus d remains a constant along the ellipse, okay? And then there are things like semi-major and minor axes, okay? I mean, I don't want to go into all details here. So you have x-axis and y-axis here. So this point here is A, and this is B, all right? If this was a circle, then there would be only one r, the radius, right? So that would be x squared plus y squared equals r squared. But for an ellipse, this condition works, and then the equation for an ellipse is x squared over a squared plus y squared over b squared equals 1. Okay, that's the equation for an ellipse. And then there are other parameters like eccentricity, and then the focal point is a certain distance away from the origin, and then the ratio of that length to a. And I mean, you can read about that, but the point is it's not a circle, and as the object goes around, the comet goes around the sun, it speeds up when it gets close to the sun and slows down when it goes away from the sun. Okay, so that's how it goes. The velocity vector is still tangential, but it's not perpendicular to r anymore. Okay, there's some angle here, not 90 degrees, which will be the case for a circle. And there is tangential acceleration as well. So a t, there's at, and there's also radial acceleration, which points to the center. Okay, well, the point is it speeds up. So when the comet is here, it's faster. V prime greater than v. Now, this all happens because of gravity, and then you can apply the potential energy. So you can compare the velocities at, let's say, let's call this here C. What color? Blue. Let's call this C. This is C. And compare the velocities here, where it is perpendicular in the y direction, then here. Let's call this V1, and let's call this V2. How am I going to do that? Well, I'm going to use the total, the mechanical energy, which is sum of kinetic and potential energy. So basically 1/2 m. M is the mass of the comet. V1 squared minus g m times mass of the sun divided by, now I need distance from the sun to the comet, which is c plus a. All right, this energy will not change. This means when the comet is on the other side, at the closest position, let's say, now it's going to have this as the energy, or this form, or this expression, 1/2 mv2 squared minus g m mass of the sun divided by, okay, this is a minus c now. This is a minus c. All right, so the solution of this equation will give you V2 in terms of V1, and you can compare all that. So if you know what the parameter C is, right? Smaller the C, smaller the parameter C, closer the ellipse to the circle. All right, so for 0C, you will have a circle. Okay, that's what we mean by eccentricity. So you can define a number called E. That would be the ratio of C to A, I think. I think it's like that. So C is E times A for, okay, I mean, it doesn't matter how we define it, but I think it's like that. So if C is small, this means you're closer to a circle. I mean, Earth has an orbit, which is an ellipse, of course, but it's close to a circle, unlike the comets, that come and go, every 70 years, the Halley, and then there was this recent comet, Atlas, right? So those are more elliptical, okay? Ellipse is the exact solution for motion in space due to gravity. Now, this is for two particles. Now, when I'm doing this, I'm ignoring the influence of other planets and other things. I mean, it's complicated. When you have two objects, you have an exact solution, analytical solution I'm talking about, not numerical or not computational. That's a different story. But once you have, let's say, three particles, okay? Let's say you have a binary star, two stars, and then a comet that goes around. That problem is complicated, okay? Just add one more to the picture, and you'll have a complicated problem with no exact, analytical solution. Many particle problems is a difficult problem, but you can use computers and solutions and approximation techniques, and then you can obtain good answers. Otherwise, you wouldn't be able to calculate the trajectories of asteroids and comets and all that, right? So Kepler did observations on planets. This was before Newton. He didn't know anything about F equals ma or Newton's gravity law. Just by looking, he was a student of Tycho Brahe. So Tycho, how do you spell Tycho Brahe? Astronomer, and his student Johannes Kepler. He had a telescope. He looked at only a handful of planets, 5, I believe. But he came up with tables, and then using brute pen and paper power without any computers, he came up with laws that govern the motion of planets around the sun. And there are 3 such laws, just like Newton's 3 laws, we have Kepler's 3 laws. So one of them has to do with the relation between the distance from the focal point, which is the sun, in our case, the distance from the sun, and the time it takes to complete one cycle around the sun, 1 year, okay? So period, it's called a period. Period, let's use the letter T for period. T, period, or year in this case. And of course, we have the distance from the sun, orbital radius. Orbital radius. So based on his observations, he found a relationship between T and R. They are proportional, but not exactly, not linearly at least, which means farther the planet, longer the year, yes, but what's the exact relation? So he came up with a fractional dependence, and Newton, when he wrote down his laws, he confirmed this, okay? So I'm going to repeat that calculation now. Just to make it easy, let's take an orbit which is a circle, okay? Without loss of generalization, I think we can do it. So that's a circle, and this is the planet with mass m. And here's the sun with mass capital M. So this orbital radius is right there between, from the center of the sun to the center of the planet, that's R. By the way, when a planet goes around the sun moves as well, okay? Believe it or not, it's not just sun at the dead center of that R or point, and the planet just goes around as if the star was pinned there. No, they both go around their center of mass. But what happens is sun is so massive. I mean, look at that, 2 times 10 to the power 30. Sun is so massive compared to the planet, even if that's Jupiter, you know, it's so massive that the center of mass actually lies within the star. So, okay, so you don't really see the sun going physically, you know, around the point which is outside the star. But if you compare this to a binary star system, 2 stars of comparable mass, then their rotation will not be like that, looking from Earth. It'll be more like this. They'll go around each other, okay? I think that's how it is. I'm not an astronomer, but anyway, so going back to Kepler and Newton. So in this case, how am I gonna find the relationship between T and R with all this, all right? And I don't even need to use the potential. I can do it without that. I can just use material from circular motion. Remember, when the object goes around a center with velocity v, there will be an acceleration which points to the center, therefore centripetal acceleration. That is equal to v squared over r. If that's the acceleration, what causes that acceleration? Newton says the answer is, of course, the gravitational attraction, which has to be in the same direction as the acceleration, and that points to the sun. That's F. And Newton's third law says F equals ma, which is v squared over r, okay? Now, Newton's third law says the net force, but in this case, we're ignoring everything else. It's just one planet and one the sun, and the only force on the planet is the attraction of the sun. So what is that? That's G times mass of the planet times mass of the sun divided by r squared, right? Inverse squared formula. Now that will be equal to the planet's mass times its velocity squared divided by r, all right? Now, period, year, is the time required to complete one cycle. And for a circle, you don't have speeding up or slowing down like you would have for a comet, you know, negligible effect because the orbit is really close to a circle. So v is a constant, okay? If v is a constant, what is the total distance along the perimeter? The circumference, right? So the circumference, which is 2 pi r. So this much in length is covered in a time equal to t, period. So you just multiply this by the velocity. So v is 2 pi r divided by t. So let's take this and plug it in the other equation there. By the way, you can get rid of m. Okay, from now on, don't worry about the planet's mass. Doesn't matter. When I find the relationship between T and R, the planet's mass will not be there. Okay, it could be Jupiter or Earth, you know. If it were able to, if it was possible to put the two on the same orbit, make no difference, all right? They would have the same speed. Anyway, so let's take this and plug it in. So I'm going to continue right here. So I have G M divided by, now there's R squared and R here. Let's get rid of the one over the R's. So GM over R is equal to V squared. That is 4 pi squared r squared, 4 pi squared r squared divided by t squared. All right, So if you rearrange these, and there's one r and two r's over there, which makes an r cubed, you will have something like gm divided by 4 pi squared times t squared is equal to r cubed. Okay, gm over 4 pi squared times t squared is equal to r cubed. Now, this is just a constant that only depends on the solar mass, not the planet's mass. But the relationship between t and r goes like this. T squared is proportional to r cubed, and that's what Kepler found before Newton. T squared proportional to the cube of the radius. All right, so using this relationship, you could find the year, my Mars year, a Martian year. You just need to know how far is Mars from the sun. Using Earth year, you can just calculate a year on Mars. All right, what else can we do with this? Well, we can take the same relation and solve for m. So let's do that. Go back to blue and solve that equation that I just wrote there for m. What is the mass of the sun? Okay, I use that number here, 2 times 10 to the 30. Let's see if indeed is the number. So the solution of m here will be 4 pi squared r cubed times r cubed divided by gm t squared. Okay, so for Earth, let's say, let's use data from Earth. We're familiar with that. 4 pi squared times r. This is the distance from Earth to the sun, 149 million kilometers, which makes 10 to the power 9 meters. And you take the cube. All right, and you divide this by g, 6.67 times 10 to the power negative 11 Newton meter squared per kilogram squared. Okay, I put an m there. That was by mistake. Sorry about that. I already have m on the other side. So get rid of this m here. All right, so going back to the pen here, okay. I need to multiply this by period squared. What is the period? Length of a year. Earth year is 1 year, which is 365.25 days, the sidereal year, okay, times that many days. Each day has 24 hours, and 1 hour is 3,600 seconds. So I'm going to square this. All right, calculator time. 4 pi squared times 149, 10 to the power 9, the cubed. Where's cubed? Right here. Cubed divided by 6.67 to the power negative 11 divided by 365.25 times 24 times 3,600 squared. 1.966 966 times 10 to the power 30 in kilograms. All right, That's how we calculate the mass of the sun. You want to calculate the mass of the moon? Just look at the the capsule, you know, in orbit around the sun. I'm sure, not the sun, about the Earth, about the moon. You can find the mass of the Earth like that easily. That's how actually you can find it. You just need the distance between the moon and the Earth. All right, okay, so using this, can you find the mass of a galaxy together? Now, all these billions of stars going around a center, a galactic center. Now we know it is a quasar and then a black hole, supermassive black hole. But we know that billions of stars go around the galactic center. This takes maybe 300 million years. The period for this is 300 million years. So this rotation rate and the size of the galaxy, if you put those together into this simple formula, or variations of it, depending on how accurate you want your calculations to be, you get a problem because you astronomically how much mass there should be using other techniques. Okay, but now using Newtonian dynamics, you can come up with a number which does not match the number you normally calculate. You would calculate. There's a maybe 1 to 10 ratio. Okay, there's this 9/10 of mass missing. We don't see it. It's not interacting us electromagnetically, or it's not emitting light. It's not blocking light. So we don't know what it is. It cannot be the regular matter, but it has mass. What is it? Okay, that's a big problem in physics. One of the major problems. And we call it dark matter. In physics, if you don't know what something is, just call it dark. Dark matter. Like dark energy, we have dark matter. Dark energy is the factor that expands the universe with an accelerating rate. Why? We don't know, but we call it dark again, dark energy. Dark energy is if you think of whole universe like a pie chart, sorry, a great portion of this is dark energy, responsible for the expansion, accelerated expansion of the universe. And this is only last 20 years, okay? This was discovered in the late 90s. Another great portion now will be this dark matter. Dark matter here. We don't know what it is, but it's there. Otherwise, you can't explain why the rotation is at that speed. And only remaining 4 or 5%, well, that's us. Stars, galaxies, things we can see, things which are made of hydrogen, helium, and other elements. That's only 4 or 5%. So most of the universe, we have no clue. All right, so I'll probably make just one more video and finish this chapter. This was Newtonian gravity, part 5. I'm gonna stop now.